Hey guys, in this video we will be talking about the greatest common factor and factoring by grouping. So consider the following product: 2 times 3 equals 6. The numbers 2 and 3 are called factors of 6, and we say that 2 times 3 is a factored form of 6. The same will be true for variables. If we have x squared times x cubed, which multiplies to x to the fifth, we call x squared and x cubed factors of x to the fifth, and we say that x squared times x cubed is a factored form of x to the fifth. And this will also be true for polynomials. If we have x plus 2 times x plus 3, multiplying this out and combining the like terms gives us x squared plus 5x plus 6. We call x plus 2 and x plus 3 factors of x squared plus 5x plus 6, and we say that x plus 2 times x plus 3 is a factored form of the polynomial. So the process of writing a polynomial as a product is called factoring the polynomial. Let's study the example below to see if we can find a pattern. The first example shows us the process of multiplying, whereas the second example shows us the process of factoring. Factoring is actually the reverse process of multiplying. So we want to find a way to start with a polynomial like this and get it into factored form. We're going to first need to go over finding the greatest common factor, also known as the GCF. So the greatest common factor of a group of 2 or more integers is the largest common factor of the numbers in the group. For example, if we want to find the GCF of 12 and 20, we can list their positive factors. So 12 and 20 have a 1 in common, and they also have a 2 and a 4 in common. However, the greatest common factor of 12 and 20 is 4, since this is the largest of the common factors. So let's try a few examples. We want to find the greatest common factor of each list of numbers. So let's list out the factors of 28 and the factors of 40. The greatest factor that they have in common will be 4. So the GCF of 28 and 40 is 4. We can do the same thing for 55 and 21. So they only have a common factor of 1. Therefore, the GCF of 55 and 21 is 1. And the same process applies for the list of 3 numbers. We list out the factors of 15, 18, and 66, and the greatest factor that they have in common is 3. So the GCF of 15, 18, and 66 is 3. Now let's talk about how we find the GCF for a list of variables raised to powers. The GCF will be found in a similar way. So let's say we wanted to find the greatest common factor of x squared, x cubed, and x to the fifth. We can start with listing out their factors, and it might be helpful to pair up each factor. So starting with x squared, 1 is a factor of x squared, and this would pair up with x squared, since 1 times x squared is equal to x squared. Then x to the first is another factor, and this would pair up with x to the first also, since x to the first times x to the first is equal to x squared. But we don't have to list this twice, so we just write x. And that's it. For x cubed, 1 is a factor, and this would pair up with x cubed, since 1 times x cubed is just equal to x cubed. X to the first is also a factor, and this would pair up with x squared, since x to the first times x squared is equal to x cubed. And that's it. Then for x to the fifth, 1 is a factor, and this would pair up with x to the 5th, since 1 times x to the 5th is just x to the 5th. X to the 1st is another factor, and this would pair up with x to the 4th, since x to the 1st times x to the 4th is equal to x to the 5th. X squared is another factor, which would pair up with x cubed, since x squared times x cubed is equal to x to the 5th. And we're done listing out our factors. So the greatest common factor of these terms is x squared. There's actually a shortcut to this. Notice how each term includes every preceding degree. This will always be the case for variables raised to powers. Therefore, the greatest common factor for a list of common variables raised to powers will be the variable with the smallest exponent in the list. So since x squared had the smallest exponent of this common list of variables, this will be our GCF. Let's use a shortcut for the next example. We want to find the GCF for the list of terms. For the first list, since there are common variables raised to powers, the GCF will be the variable with the smallest exponent of the list, so x cubed. And for the next example, we can use the same shortcut. The greatest common factor will be y to the 1st, or simply y, since 1 is the smallest exponent on y. So the greatest common factor of a list of terms is the product of the GCF of the numerical coefficients and the GCF of the variable factors. So if we wanted to find the GCF for the following terms, we first find the GCF for the numerical coefficients, which is 2. Then we find the GCF for x squared and x, which is x since it has a smaller exponent. And the GCF between y squared and y cubed is y squared. Therefore, the GCF of these two terms is 2xy to the 2nd. So for example 3, we want to find the GCF of each list of terms. First, we find the GCF of the numerical coefficients 6, 10, and -8. The GCF will be 2. We could also say that the GCF is -2, but for now, let's just list it as a positive GCF. Then the GCF for the variable factor, x, will just be that variable with the smallest exponent of the list, so x. Therefore, the GCF of these three terms is 2x. We do the same procedure for the next example, so the GCF of -18, -63, and 27 is 9. Then the GCF for the variable factor y is y squared, since it has the smaller exponent. So our GCF for these three terms is 9y squared. And for the last example, the GCF for the numerical coefficient is just 1. Then for the variable a, the GCF is a cubed. The GCF for the variable b is just b. But for c, since the variable does not show up in the other two terms, we do not include it as part of the GCF. Therefore, our GCF for these three terms is a cubed b. Now let's see how we can use the GCF to factor polynomials. In order to factor a polynomial, we must write it as a product of two or more polynomials. And the first step will always be to factor out the GCF from the polynomial. So consider the following polynomial of the form 8x plus 14. We first see whether the terms have a GCF other than 1. The GCF of 8x and 14 is 2, and we could rewrite our terms with this GCF of 2. So we factor out the 2 from each term, and in parentheses, we write what remains. Therefore, our factored polynomial of 8x plus 14 is 2 times 4x plus 7, where 2 is one factor and 4x plus 7 is the other factor. We can always check if we factor the polynomial correctly by multiplying. The result should be the original polynomial, ax plus 14, which it is. Okay, let's try a few examples. We want to factor the polynomial by factoring out the GCF. So the first step would be to find the GCF of 5xy and 10x. That would be 5x. So we can rewrite the terms as factors with this GCF, and then we can factor out the GCF of 5x, and write what remains in parentheses. Now that our expression is written as a product of two factors, we have factored the polynomial. And we can always check to see if this is correctly factored by multiplying. Multiplying this out, we get our original polynomial. Therefore, this is the correct factored form. For the next example, we apply the same procedure. We must first find the GCF of our terms. This will be 6x cubed. So we can rewrite the terms as factors with this GCF, and then factor out the GCF of 6x cubed, and write what remains in parentheses. Now we have factored out the GCF. We can also check this by multiplying out, and since we get our original expression after multiplying, this is the correct factored form. And then for the next example, the GCF of the four terms is going to be 4x cubed y. So we can rewrite each term as factors first with this GCF, and then factor out the GCF of 4x cubed y, and write what remains in parentheses. And now we have factored out the GCF. By the way, we could have also made the GCF negative 4x cubed y instead. Both will be correct. So if instead we factored out a negative 4x cubed y, we would just change the signs accordingly. And again, you can always check this by making sure it multiplies to the original polynomial above, which it will. Okay, so far the GCF has been a monomial, or one term. Sometimes the GCF is a binomial, or two terms. So let's go over an example of such a case. So for example 5, we want to factor out the GCF. Notice how these two terms have x plus 2 in common. This will be our GCF that we factor out. So we factor out the GCF x plus 2 and write what remains next to it in parentheses. We have now factored out the GCF. And the same thing for the next one. Notice how these two terms have a y plus 4 in common. This will be the GCF. So we factor out the GCF, y plus 4, and write what remains next to it in parentheses. Be careful. There is technically a 1 here, so then y minus 1 remains. And now we have factored out the GCF. This will now lead us to the next method of factoring, which is factoring by grouping. So in order to factor a polynomial with 4 terms, we normally would factor by grouping, where we group the terms into 2 groups of 2 terms, so that each group has a common factor. And then we factor out the GCF from each group. And if there is a common binomial, we factor it out. And if not, then rearrange the terms and try again. Otherwise, it may not be factorable, which is possible. Okay, so let's try factoring the following example by grouping. First, we group this into 2 groups, and then we find the GCF from each group and factor it out. The GCF from the first group is x, and the GCF from the second group is 3. We factor out the GCF from each group and write what remains. So we factor out the x from the first group, and y plus 2 remains. Next, we bring down the plus sign, and factor out 3 from the second group, and y plus 2 remains. Now notice that there is a common binomial of y plus 2. We factor this out, and we write what remains next to it in parentheses. And now we are done. Our polynomial is factored. Let's try another example. We want to factor the following polynomial by grouping. So we group this into two groups. The GCF for the first group is x, and the GCF for the second group is 1, since they have no other common factors. Factor out the x from the first group, and we have 3x plus 4y left over. Bring down the minus sign, and then we factor out 1 from the next group. But be careful, now we are factoring out a negative 1, so we need to adjust the signs accordingly of what remains. So positive 3x plus 4y remains. Now we have a common binomial of 3x plus 4y, and we can factor this out. And x minus 1 remains. And now our polynomial is factored.